Hello, in this video we're going to talk about deletion of B plus tree. So here is an example B plus tree. It has the root node and it has 6 leaf nodes. Okay, so we need to first find out the location of what we're trying to delete. So the first one we're going to delete is Spring Boson. So you can just look at it and you can find it, but obviously you will want to go to the root. Since S is later than N, we're going to follow this one, and then we see that it's actually one of the index values. So it's here, right? So we can delete this here. So just to recap the memory, the two rules of having a balanced tree in a B plus tree is that the root node has to have at least 2 children, which it does, and each of these leaf nodes has to be at least half full. So you can see that these are all at least half full. This is until we delete this. So that we only have 1 out of 3. So that's only 33%. It does break the rule. Okay, so you have two options. The first thing you need to consider is that are you able to borrow from either of your neighbors? So your neighbor means either the node right here on the right side or the left side. So this one, if we borrow Sing from this one, this will only have 1 out of 3, so we're not able to borrow. Here we don't have any neighbors, so this is our only neighbor, and we're clearly not able to borrow. So the last option to consider is to merge with your neighbor. So once we delete this value from this node, we only have Wu, and because of that, it's not half full. So we're gonna combine Wu with this neighbor. So now we'll have Mozart, Sing, and Wu. Okay. The next value is to delete Sing. Okay, so we see that Sing is here. After deleting this value, we have Mozart and Wu. That's 2 out of 3, so it is half full, so it's still good. Okay, so now when we try to delete Wu from here as well, after deleting Sing, we'll only have Mozart in this node. That's only 1 out of 3. Not a good option. So the first thing you want to consider is to borrow from your neighbor, and we see that there's no right neighbor, there's only this neighbor. If we borrow 1 out of 3, this will still be good because it'll be 2 out of 3, at least half. So we're going to borrow Kim, and then we're going to move that into this node. So now this will have gold and cats, and this will have Kim and Mozart. And based on that, because now the biggest value from this node is Kim, we do have to update this index value to be Kim. The next value we're going to delete is gold. Okay, so gold is right here. Also notice that gold is one of the index values. Okay, so what happens if you delete gold? So gold, if you delete gold, this is only 1 out of 3. It's not going to be half full. We cannot borrow from this or this because they will have only 1 out of 3 if they let us borrow. So that's not an option. So that means we have to combine with one of our neighbors. So this will only have cats left. So you could merge this one and this one, or you could merge this one and this one. I tend to go with the easier looking ones because this node is kind of on the other side of this, so I'm gonna just choose to merge with this one. So now I'll have Cat, Kim, and Mozart, right? So because now gold is gone, I'm gonna delete this index value. Okay, and we have lost a node, right? We used to originally have 5 nodes, and now I have 4. So we have lost a node, a leaf node. So that means you also have to lose an index value. Okay, so that's going to be gold because now we don't have the value gold because we just deleted it. Okay, so now this still has, so once you delete this, this is what you're going to get. Okay, so whenever you remove something and it's still half full, that's great. If not, you want to try to borrow from either your left or your right neighbor. Okay, so we want to check to see, if they let us borrow one, are they still going to be half full? If they are, then you can borrow. If not, you want to consider merging with either of the neighbors. Okay. So let's try deleting 70 from this tree. 70 is greater than 60, so I'm going to follow this pointer. And then 70 is less than 75, so I'm going to follow this pointer right here, and it's pointing to this one. So I have deleted 70 from this one, right? So now I'm left with 60 and 65. That's 2 out of 4. So this is 50% full. We want it to be at least half full. So it still doesn't break the rule. It's still V plus 3. It's still balanced. Okay, so that was a simple delete. Next, we want to try to delete 25. Okay? So 25 is less than 60. Follow this node. Notice how 25 is an index value. I'm going to follow this. So I'm going to delete this one, 25. Once I delete 25, I am left with 28 and 30. That's 2 out of 4. So this is still 50% full. One thing to pay attention to is this index value right here. This value should be the biggest value, or actually the smallest value from this node. So after deleting 25, 28 will now be the biggest value. So don't forget to delete or modify your update, your index. So this 25 should now be 28. Okay, next value to delete is 60, and you can already see that 60 is an index value. So follow the node, and then here is 60. So once I delete 60, I only have 1 out of 4. That's only 25% full. Let's see if we can borrow from this neighbor or this neighbor, and we're not able to because they're right now at 50%. So they're not able to lend us anything. So that means we're going to have to merge with one of our neighbors. So after deleting 60, this one only has 65. So this 65 could be merged with this one or this one. So either way, it's not wrong. It's really your choice. Okay, so we're gonna merge. So you could have merged with this node. So it would have 65, 75, and 80. This example right now is merging with this one, which has 50, 55, and then now it'll be 65. Okay, so we have merged these two nodes. So now we went from having 6 leaf nodes to now 5. Okay, so whenever you lose a node, you also need to lose an index value. And in our case, it's going to be 60, right? Because we had 60 as our index value. And then the root node will have these 4 index values. Okay, so I think in a way, deletion may be a little bit easier than adding a value, but that's, I don't know, it depends on the person. I feel like it's easier. Okay, so these are the 3 cases I talked about. When once you delete something and it's still at 50%, that's the easiest. You don't have to do anything. You don't have to merge with someone or borrow from someone or update any index values. It's easy. So this one, you want to try to borrow from a neighbor. If that doesn't work, you want to try to merge with a neighbor. Okay, so the complexity of having these updates. So update means inserting or deleting. Okay, so for a single entry, is proportional to the height of the tree. Okay, so this one has 3 levels. So if you have a really high one, there's gonna be more operations and index values to consider. Okay, so that's gonna be big O log n over 2 ceiling function k. But in practice, number of input-output operations is less. Internal nodes tend to be a buffer, and splitting and merging are rare. So most inserts and deletes operations only affect only the leaf nodes. And 2/3 with random and half with insertion in sorted order. Okay, so variable length strings as keys. So you can use the variable length strings as a key. So here, key values in the internal nodes can be prefixed of full key. So keep enough characters to distinguish entries in the subtrees separated by the key values. So we have Silas and Silver's Sweats. This can be separated by silb, which would be going in between these two. But a lot of the examples or even the exams, we're not going to deal with these strings or letters. We're going to be doing mostly numbers. It's just easier and less things to write. So let's take a look at this exercise. We have a tree, and let's try to think about what the value of n is. So what is the value of n here? Is it 3? Okay, so we have 3 key values that you can fit in. It also has a pointer here, another pointer in between, another pointer, and another pointer. We have 1, 2, 3, 4 pointers, right? So that means the value of n here is 4. So you can fit up to 3. The root node has to have at least 2 children. It has 3. And then each of these nodes have to be at least half full, and they are. So from this tree, we are going to try to remove 28, 4, 7, and 2 in this order. Okay, so again, just like the addition, especially on the exam or homework, try to show each level, like the resulting tree after removing 28, and then try to draw another one after removing 4, and so on, showing each step. So that way, if you mess up on just removing 4, and these were right, I only take points off for this one. Okay, so let's go to the first one, removing 28. 28 is greater than 17, so I follow the pointer. I go to this node. I'm going to delete 28. So after deleting 28, I still have 17 and 21. That's still 2 out of 3, still half full. It's an easy delete. Okay. After that is 4. Okay, so 4 is less than 7. I follow the pointer. I go to this node. Once I delete 4 from this node, I will only have 1 out of 3, which is not half full. So I'm going to consider borrowing from a neighbor. I only have one neighbor here. This neighbor is 2 out of 3. If I borrow 7, this will not be half full. So I'm not able to borrow. So the next option is to merge, right? So after deleting 4, this only has 2. So 2 will be merged with this node. So it'll be 2, 7, and 10. So we initially had 3 nodes. Now we have 2. One that has 2, 7, and 10, and then the other one is this one. So whenever you lose a node, you also lose an index value. Make sure you remember that and you delete the index value. Okay, so this one has 2, 7, and 10. And this will have 17 and 21. So that means we're going to be deleting this index value, 7. Okay, next is 7. We're deleting 7. Okay, so from here, let's see. 7 is less than 17. I follow the pointer and 7 is right here. So after deleting 7, it will have 2 and 10. 2 out of 3. Still half full, so it's a simple delete is 7. Okay, the very last value we're going to delete is 2. 2 is less than 17. I follow the pointer, go to this node, and I'm going to delete 2. So after deleting 2, I only have one value out of 3, which is not half full. I cannot borrow from this guy, so I'm going to merge. So it will have 10, 17, and 21. So we have gone from having 2 nodes to just 1. That means we lose the index value, right? And we'll only have a single node that contains 10, 17, and 21. This is your final answer. Okay, so here is another example. So go ahead and try removing 9, 7, and 8 from this tree. And once you're done, click finish or hit play again. Okay, so here the first value to delete is 9, and I noticed that 9 is one of our index values. It is a root node. Okay, so 9, follow this one, and then I have found 9. I'm going to delete this 9. It's not half full. It only has 1 out of 3. I cannot borrow from this one because it will be only 1 out of 3. Same thing with here. So I'm not able to borrow from either of these guys. Okay, so the next option is I could either merge with this node or with this node. So really depends on what you prefer to do. Let's see what this example will. Okay, I guess it decided to merge with the right one, right? Yeah. Okay, so it's gonna delete 9. We only have 10. So 10 will be merged with this right neighbor, which has 11 and 12. So now I have 10, 11, and 12. Okay, so whenever we lose a node because we combine these two into one, we have to delete an index value, right? So we're gonna look at the smallest value from each node. So this one is 3, 5, and then 7, and then 10. Okay, so we have gotten rid of one of the index values, okay, and it is balanced, right? Because this root node has 2 children, and then each of these are half full, at least half full, at least half full. This is totally full. Okay, next we're gonna remove 7. Okay, let's take a look. So 7 again is actually the root node. It's an index value, and we see the 7 here. So I'm gonna get rid of 7. Now I only have one value out of 3. It's not half full. Let's see if I can borrow from this node. I'm not, because they only have 2. They give 1, they'll only have 1 out of 3. Not a good option. I'm going to go to this one. They actually have 3 values out of 3, so we are able to borrow 1. Okay, so I'm actually going to borrow 10. So this will have 8 and 10, and this will have 11 and 12. Okay, so 8 and 10, 11 and 12. So based on that, we have to update these index values. This one has 8 and 10, so we have to update this to be 8. This one has 11 and 12, so this has to be updated to 11. Okay, so after removing 8, so the next value to remove is 8. 8 again is the root node, it's an index. Yeah, and 8 is right here. So I'm going to get rid of 8, so this will only have 10. I can't borrow from here or here. Okay, so I'm going to have to merge with either this one or this one. So you might have different answers. Yours might look different than mine depending on which one you choose to merge with. So this one now currently only has 10. So you can merge 10 with this one or this one. The example we use, that's actually what I would have gone with because it's just easier. So 10 is merged with 11 and 12. So now I have 10, 11, and 12. The rest stay the same, as you can see. Because we lost a node, we went from 2 nodes to 1, we do have to delete an index value. Okay, so we have 3, 5, and then 10. So you get these index values from the actual leaf nodes. So the smallest value of each leaf node is actually the index value that you're going to be using. We have 10, 5, and 3. Okay, so we have remove 4 from here. Okay, so 4 is greater than, or it's actually between 3 and 5. I don't know what happened to it. Okay, so 4. So I got rid of 4 here. Okay, so after getting rid of 4, I only have 1 out of 3. I cannot borrow from this or this, so I'm going to have to merge with 1. So after getting rid of 4, I am only left with 3. So 3 could be merged with 1 and 2, or it could be merged with 5 and 6. So depending on what you do, yours might look different. So this example, I guess, is merging with the right neighbor, which has 5 and 6. So now we have 3, 5, 6. This stays the same. This one also stays the same. And because we went from these 2 nodes to 1, we have lost a node, meaning we're going to lose an index value. So 3 and then 10. So these index values were pulled from each of these nodes. It's the smallest values from each node.